This video will serve as an introduction to the study of organic chemistry that we are about to embark upon together. Our learning goals for this lesson are that once we're done, you'll be able to define an organic substance, describe how organic compounds fit into your prior understanding of the classification of matter, identify a substance as either organic or inorganic, and finally to describe the structure of an atom, and relate the number of subatomic particles to the elemental identity, mass, and charge of an atom. So you can see there'll be some new topics discussed in this lecture and then some review from Chem 1A mostly, so the first semester of general chemistry. Let's get started. In your own words, based on what you know right now, we don't need the internet. We don't need anything but our own knowledge. And if you're working with another organic chemistry student, you certainly can discuss with that person. But first, write down your answer to this question. What is organic chemistry? I get lots of different answers when I ask this question in class, and I'm going to write down a few of those responses. If you're still working, make sure that you really do this. You write down your answer to this question. The common answers that I usually hear from students is that organic chemistry is the study of the molecules of life, molecules with carbon, or natural substances. Whatever you wrote down, it's perfectly fine because I asked what you know. I didn't ask the right answer. What we can certainly say, however, is that organic chemistry will be the study of organic compounds. Let's figure out, what are organic compounds? Let's think about what we already know about the classification of matter. Organic compounds are certainly matter. Let's go ahead and label this flowchart. We're going to use these labels, put them where they belong in the flowchart, and then once you have the labels where they belong, go ahead and define each of the terms and list examples. Please stop and do this. For this class to work, you will have to follow my directions, even though I am not there to physically enforce it. So please stop and do this. What I have written here should be pretty consistent with what you learned in general chemistry. Let's take a look. So matter is anything that is physically real, which means it takes up space and has a mass. Takes up space just means it has a volume. So not energy, but pretty much everything else, right? The two big groups of matter that you discussed in general chemistry were elements and compounds. An element is a fundamental substance that can't be turned into a simpler substance by chemical means, and we find elements on the periodic table. For example, carbon, hydrogen, oxygen, nitrogen, sodium, magnesium. This is fun. These are all elements. We can tell because there's one symbol in their chemical formula. Now, compounds are made up of two or more elements in a defined ratio. Some examples of compounds would be hydrogen peroxide, which is always 2 atoms of hydrogen and 2 atoms of oxygen, or sodium chloride, which is always formed in a 1-to-1 ratio of sodium to chloride atoms. There are molecular compounds and ionic compounds. Molecular compounds contain covalent bonds, and usually these are made of nonmetals bonding with one another. Examples of molecular compounds would be hydrogen peroxide that I listed up above, methane, CH4, carbon dioxide, CO2. Ionic compounds. Well, ionic compounds contain ionic bonds. So what that means is that they are made up of a cation and an anion. And I suspect that many of you in your definition maybe wrote that they were made up of a metal and a nonmetal. Often they are made up of a metal that has formed a cation and a nonmetal that has gained electrons to form an anion, but not always. Ionic compounds are made up of ions. That is the general definition. And you saw that with ammonium chloride. There's only nonmetals in that ionic compound, but it's still an ionic compound because ammonium is a cation and chloride is an anion. Another example would be sodium chloride. that I had listed as a general example of a compound above. Now that we have this down, let's take a look and consider this question. Where do organic molecules fit in this chart? You should stop the video and add them to your chart and then write down your reasoning. Don't skip this part. Please go ahead and do it. This is your last chance if you haven't already done it. Okay, wherever you put them, wherever you put organic compounds is fine, as long as you put them somewhere under compound, then it's fine. All right, let's move on. We're going to come back to it, don't worry. So let's just define an organic compound, just like we defined molecular and ionic compounds on the previous slide. So what is an organic compound? Organic compounds were originally defined as compounds made by organisms, by living things. The modern definition of organic compounds, however, are those that are made out of at least carbon and hydrogen, and maybe some other elements. Those other elements may be oxygen, nitrogen, sulfur, phosphorus, chlorine, and some others. Now, why don't we define organic compounds as they were originally defined, such as those that are made by living things? Well, this definition broke down when chemists discovered that ammonium cyanate could be heated in the laboratory to form urea. Let's go ahead and classify ammonium cyanate and urea so that we can understand why this changed the definition of organic compounds. Pause and do that. Ammonium cyanate is an ionic compound. It's made from the ammonium and cyanate ions. Notice this is an example of an ionic compound made entirely of nonmetals, but it is made of ions, so it is an ionic compound. Ammonium cyanate is also an inorganic compound. It does not contain carbon and hydrogen. Now, if I stop speaking now, you might say, hey, yes, it does. Here's hydrogen, here's carbon. They must be in the same unit in order for the substance to be organic. So the hydrogen is here in ammonium, and the carbon is over here in cyanate. Yes, Lewis structures. They're coming back, folks. It is not an organic compound. It is an inorganic compound. But when it's heated, it forms urea, and urea is a molecular compound. You can see it contains covalent bonds. All the bonds in this molecule, all the bonds in this substance are between nonmetals. And I haven't shown them all. It's not a complete Lewis structure. I also ignored the lone pairs, and you will start to ignore lone pairs too as we progress in the class. But it contains covalent bonds. It is also an organic compound. It's an organic compound because hydrogen and carbon are contained in the same unit. So because chemists could make urea in the lab, they realized that organic compounds are not just compounds made by living things. They are compounds that contain carbon and hydrogen and maybe some other element. Excellent. Have we figured out now where to put organic compounds in our flowchart? What do you think? Where should they go? Well, before we make any commitment, allow me to provide you with one more piece of data. If urea is treated with sodium hydroxide, a proton transfer reaction occurs because sodium hydroxide, as you know from Chem 1b, is a base, and urea is reasonably acidic. What results from this proton transfer reaction? Has a structure that looks like this. And of course, we've made water. Excellent. We've made a salt of urea. So how would you classify this substance? What is its classification? Is it molecular or ionic? Yeah, it certainly contains both covalent and ionic bonds. Is it organic or inorganic? Well, it's certainly organic. It has carbon and hydrogen. So it's an organic compound. Oh, did this mess up anybody's classification of matter? Did anybody want to say that all organic compounds were molecular? Can we do that now? Well, no. Now this organic compound contains an ionic bond. Let's point to it. There it is. Opposites attract. So matter can be classified in different ways. And for this class, we might consider a different flowchart. What might that flowchart look like? Perhaps we should consider a flowchart like this, where we consider organic versus inorganic compounds instead of ionic versus covalent. And that, of course, is because although all organic compounds contain carbon and hydrogen, and maybe some other elements like oxygen, we know they contain covalent bonds as well. They may also be ionized. And all the variations in whether or not the compounds are ionized, what types of bonds the organic compounds have, will make all of these new groups, all of these new ways to classify organic compounds within this big group. And that's what we'll learn about this semester, all the different families of organic compounds and their properties and reactivities. We will be as organized and look for as many patterns as possible so you feel like you're seeing a big picture and you're not memorizing a lot of little things. We'll begin our study of organic compounds with a few familiar molecules. Do you recognize any of these? How would you classify them? Are they organic or inorganic? Are they molecular or ionic? And does any of it matter? Take a moment, take a look, see what you can come up with. You may have recognized these first two molecules. They are both glucose. Here we have glucose in its open chain form and in its closed chain form. We will talk much more about this in Chem 12B. We have glucose. Glucose is certainly an organic molecule. It contains many carbons and hydrogens. I'll highlight some of them. Now, in the closed chain form, I used a different way of representing the molecule. I used a skeletal structure where the carbon atoms are implied. But all of these ends, each end and bend is a carbon atom. And then, of course, there are many hydrogens in this molecule. So this is certainly organic, and it contains covalent bonds. There are no ionic bonds in this particular molecule. That's in contrast to this compound. This compound is also organic. It contains many carbons and hydrogens. You can point them out, but it also contains covalent and ionic in ionized regions. So I didn't actually put any counter ions, but we can throw some sodiums here, and then we can see we have some ionic interactions. But yes, it contains covalent and ionic bonds. Did anyone recognize this molecule? Yeah, it's a nucleotide. Do you know which one? Oh, you can see it's a purine. If you've already had Bio 60, you might recognize some of these words. So it's a purine. All right, how about this? This is acetone. It is a component of fingernail polish remover and a very common solvent. Lots of carbons and hydrogens in that structure, and you can see all covalent bonds. You should be pretty familiar with this molecule, perhaps, especially if you had Bio 60. That's an amino acid. Specifically, it is alanine. You can tell from this methyl side chain. Alanine is ionized. You can see ionized. So it's an organic compound for sure, and it contains covalent ionic bonds as well. And finally, we have this molecule. Many students recognize the steroid core, either often from Bio 60 or just from your other life experiences. So this is the steroid core, and this particular steroid is estradiol, which is a sex hormone, and it is an organic molecule. We can see lots of carbons and hydrogens. Again, there's a lot of carbon, and so I showed the structure in its skeletal or bond line representation, where all those carbons are implied. Oh, there's another one right there. And then I will not highlight any hydrogens, but you can see them. And then, of course, there are enough hydrogens on each of these implied carbons so that they all have full octets. And we will talk much more about that. I hope that these biomolecules in acetone give you a sense of the diversity in the structures and the types of bonds in organic compounds. Of course, does any of it matter? Yes, it matters tremendously. Whether or not glucose is in its closed chain or open chain affects its properties. The fact that the nucleotide is ionized certainly affects its properties. We could list structural features of these molecules for hours, and we will later in the course. Let's think about something that each of these molecules have in common. What is it? Carbon. Why are the molecules of life based on carbon? Stop, think, and then write down your answer. Please pause and do that, and then rejoin me. Whatever you came up with sounds good to me. Let's discuss together now. So the first aspect of carbon that makes it so suitable to form the rich diversity of the compounds that make up living organisms is that it can make 4 bonds. What's the fancy word for makes 4 bonds? Yes, it's tetravalent. And not only can it make lots of different bonds, it can make a wide variety of bonding types. So we could have single bonds in a chain. We could throw some double bonds in there, and I'm just showing carbon. I'm not showing hydrogen or any other elements right now. We could have carbon can make triple bonds. Because carbon makes 4 bonds to achieve a complete octet, there's a wide variety of ways in which it can do that, and thus a rich diversity of compounds based on carbon exist. In fact, there are over 70 million known organic compounds. And many of those you can actually buy at the chemical store. Not you, but if you become a researcher and you run a lab, you can buy many of these organic compounds at the chemical store and then do all kinds of great things with them, like build materials or pharmaceuticals or advanced basic science. Second, carbon makes strong bonds. The bond strength of a carbon-carbon bond is about 81 kcals per mole. I like to use kcals. Most chemists like to use kilojoules, but maybe I'm a biologist in secret. I like to use kcals. The carbon-hydrogen bond has a bond strength of about 100 kcals per mole. So these are strong bonds. What if, however, we discovered life on another planet and it was based on an element other than carbon? What do you think that element is most likely to be? This is always fun. What do you think? Well, which element has the most in common with carbon? What do you remember from general chemistry? Yes, that elements in the same group have this similar chemical and physical properties. So that means that silicon might be a candidate for forming molecules of life on a different planet because it is also tetravalent. I mean, it also forms 4 bonds to make a complete octet of electrons around it. That is similar to carbon, but what about bond strength? Well, a silicon-silicon bond is significantly weaker than a carbon-carbon bond. It has a bond strength of about 53 kilocalories per mole. And then my favorite part is to imagine respiration with silicon-based glucose. So we know respiration from Bio60, and if we were in person, I would torture you and threaten to tell Professor Herrick or whoever your Bio60 professor was when you cannot remember the chemical equation for respiration. Very sad to miss that discussion. All right, so here's the glucose reacting with oxygen to make carbon dioxide and water. We take this nice organic compound and it makes two inorganic products. We know that carbon dioxide is the waste product of metabolism, and we eliminate it from our bodies via exhalation. Breathe it out through our lungs. Now, if we had the silicon version of glucose, which of course nobody says that life that was based in silicon would work the same ways and have the same metabolic processes, that's a little bit absurd. However, it is extremely fun to think about it. Instead of carbon dioxide as the waste product, we have this molecule. Anybody recognize this molecule? Sand. Who wants to have a bunch of sand in their lungs? How are we going to get that out? Just coughing out sand. Yeah, okay. For me, this is hilarious. For you, maybe not. So clearly, if there's silicon-based life, like I believe there is in Star Trek, or for realsies, it's going to need different metabolic processes, right? But silicon can make four bonds. Unfortunately, those bonds are weak. Life on Earth is based on carbon. Carbon is tetravalent, meaning it makes four bonds to get its complete octet. And so there's a variety of bonding patterns, and thus a rich number and diversity of organic compounds. And it makes strong bonds. So these are stable compounds that don't just randomly break down in our body. That's great, unless we want them to, or unless there's a biochemical process to do so, like respiration. And then we get lots of energy out of it. All right, we're going to transition now into a bit of a review that will set you up for our next lesson. So please stop this video and draw a picture of a carbon-12 atom. Then label all the subatomic particles and anything else that you think might be important. Please pause. Remember, I got to follow my directions, even though I can't make you. Here is my carbon-12 atom. The 12 in carbon-12 is the mass of this particular atom. The mass of an atom results from the protons and the neutrons. I know that every carbon atom has 6 protons because it is atomic number 6, and the number of protons define the elemental identity of an atom. Now, this is a neutral atom because it doesn't say otherwise. Thus, the number of electrons is equal to the number of protons. This carbon atom has 6 electrons. The protons and neutrons are in the nucleus, and then the electrons are around the atom in the electron cloud. Now, obviously, this atom is not at all drawn to scale because the electron cloud takes up a space about 10 to the 5th times larger than the nucleus. It's like if the nucleus were a grape on the pitching mound of Dodger Stadium, the rest of the stadium represents the electron cloud. Great, that's a blast from the past, right? What part is most important for organic chemistry? What do you think? All of it. You're a chemist, you should know all of it. But what part is most important? The electrons. Yes, chemistry is all about the electrons. So we will talk a lot about electrons this term. Speaking of general chemistry, many of you had to memorize the names and symbols and details about many of these elements. Some of you may have had to memorize the entire periodic table. I have good news for you. In organic chemistry, we will deal with a much smaller number of elements. Typically, these elements that I have here on the organic chemist periodic table. Are we all celebrating? Yes, we should be. But I will expect that you know where, and really where just means that you know the number of valence electrons, and you might need to know the relative rows, say, of the halogens. You would need to know that fluorine is in row 2, chlorine is in row 3, and bromine is in row 4. That's mostly so you know that fluorine is smaller and iodine is bigger, speaking of atomic radius. Okay, so I expect that you pretty well have memorized the organic chemist periodic table. For example, I don't provide a periodic table on exams, but you do need to know that fluorine is smaller than iodine to answer some of the questions correctly. And you need to know the relative electronegativity of atoms. So you do need to have the organic chemist periodic table in your mind, especially for these elements. All right, like I said, a little bit of preview of what's to come. Let's get back to those electrons. So we will come back to this theme many times in this course. Electrons go to the lowest energy orbital possible, period, always, unless they are forced to do otherwise. What does that mean? You'll need to review. Quantum mechanics. In this picture of the carbon-12 atom that I just drew an electron cloud, right? But I'm going to want to know, where is this electron? What is its energy? What shape is the orbital that it's in? So you will need to review those topics from general chemistry, and I am here to help you. As our last act today, let's just make sure that we can meet one of our learning goals, which is to classify molecules as organic versus inorganic, and recognize covalent and ionic bonds within those substances. So take a moment and analyze each of these substances, classify them in as many categories that apply. Here are my answers. Make sure that you are in agreement with me, or then if you're not, that we have a discussion about it. Carbon dioxide is an inorganic compound. There's carbon, but no hydrogen. It is the waste product of a bioprocess, right? It's the waste product of metabolism. Your book indicates there might be some argument over whether or not it's organic. It's not. There's no argument. There's no hydrogen. It's inorganic. Let me know if there are any questions. Our last step for any lesson will be to revisit the learning goals, make sure we've met them, and then to reflect and summarize. You do not want to skip these steps because this is how you make some connections in your brain, and it's how you know whether or not you actually learned something and what you need to go practice. So do not skip this step. Be sure that you're able to define an organic substance. The basic gist was that it contains carbon, hydrogen, and maybe some other elements. Describe how organic compounds fit into your understanding of the classification of matter. My basic point was that usually these are molecular substances because they always contain covalent bonds, but they may be ionized. And that's important because that ionization will affect their properties as we are going to discuss in detail as we progress in the class. Identify a substance as organic or inorganic. Well, organic will contain carbon and hydrogen. Inorganic does not contain carbon and hydrogen. And to describe the structure of an atom and relate the number of subatomic particles to the elemental ID, the mass in charge of the atom. This is what we did when we drew the carbon atom. The elemental identity is the number of protons, the mass is the number of protons and electrons, and the charge of the atom has to deal with the number of protons versus the number of electrons. When you have more electrons than protons, you have an anion. When you have more protons than electrons, you'll have a cation. Let's summarize and reflect. Take a moment to write down what you learned today, how it relates to things you've learned in the past, and finally, what questions you still have.